Everything you were taught about the nature of reality may rest on a foundation that Einstein himself was not satisfied with. He spent the last 30 years of his life trying to fix it. He failed, or at least he was believed to have failed. The papers he filled with equations in the final months before his death in 1955 were, according to his colleagues, a tangle of ideas that did not quite connect. The equations sat in archives. They were studied, quoted, and occasionally dismissed. Until a machine learning system, designed for theoretical physics research, was given access to the full corpus of his late work and asked, in effect, what he had been trying to say. The output, according to the physicists reviewing it, was not gibberish. It was a structure, a framework, and it pointed somewhere uncomfortable. The equation Einstein was chasing is usually called the unified field theory. The problem is old and well known. His theory of general relativity, published in 1915, describes gravity as the curvature of spacetime by mass and energy. It works beautifully on the scale of planets, stars, and galaxies. Our GPS satellites need to account for its effects every second to give you an accurate position. It has survived every test thrown at it for more than a century. But at very small scales, the atomic and subatomic, general relativity does not describe what is happening. That job belongs to quantum mechanics, a theory with equally powerful predictions and equally strong experimental backing. The two theories use different math, describe different objects, and do not currently reconcile. Einstein believed they must. He spent the rest of his life trying to build the bridge. He worked in relative isolation. By the 1940s and 1950s, most of the physics community had moved on to quantum field theory, to particle accelerators, to the immediate problems of the post-war era. Einstein, at Princeton, kept going. He wrote letters. He filled notebooks. He proposed a series of candidate theories, most of which failed under scrutiny. At the end of his life, he told a colleague that he was still convinced the unification was possible, and that the tools to achieve it probably had not been invented yet. That is where the new analysis comes in. A research group has used a pattern recognition system trained on the full mathematical literature. You have 20th and 21st century physics to read Einstein's late notebooks as a single coherent body of work, rather than as a sequence of failed drafts. The system is good at seeing relationships that a human reviewer, reading page by page, might miss. It looked at the symbols he used, the transformations he applied, the dead ends he kept returning to, and it flagged, something that the original reviewers had apparently treated as noise. A recurring structural motif, a symmetry principle Einstein kept reaching for but never quite formalized, appears to map, surprisingly well, onto mathematical frameworks developed decades after his death. In particular, frameworks related to information geometry and certain branches of string theory that were not available to him in any form. In plain language, the analysis suggests that Einstein was not failing. He was working toward a structure that did not exist yet, using the tools he had. When the modern frameworks are overlaid onto his late equations, parts of the structure line up. Not all of it. There are still gaps. There are still places where his intuition went sideways. But the outline is there, and it resembles the picture that contemporary theoretical physics is slowly assembling. That alone would be a good historical story, a quiet vindication of the old man in Princeton. But the more interesting part is what the unified structure, read forward, seems to imply about the nature of reality itself. Einstein's core intuition, and one that he stated repeatedly, was that the universe at its deepest level should not contain arbitrary rules. There should not be one law for gravity, another for electromagnetism, another for the weak force, and so on. There should be one underlying geometry, and the forces we observe should be features of that geometry. Different expressions of the same shape. Most physicists still believe this in some form. Theories like string theory, loop quantum gravity, and various candidate models of quantum gravity all try to get there by different routes. Einstein's notebooks, according to this new reading, were pointing at a version of the same destination, but from an angle nobody had fully appreciated. The angle he kept circling back to involved information. Not information in the casual sense, but information in the precise mathematical sense developed decades later by Claude Shannon and extended into physics by researchers like John Wheeler. The idea that at the most fundamental level, the universe is not made of particles, not made of fields, not made of space-time itself, but made of relationships, distinguishable states that can be compared to other distinguishable states. Matter, energy, and even geometry could then be emergent consequences of those relationships. The universe in this picture is closer to a structure of answers than a structure of things. Modern versions of this idea are sometimes called "it from bit" physics, a phrase Wheeler coined in the 1980s. They are taken very seriously today. They underlie the holographic principle, the proposal that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary, which has been confirmed in specific model universes and is considered by many theorists to be a property of our own. They underlie the growing research program that treats space-time itself as something woven from quantum entanglement. And, according to the new analysis, they appear to be what Einstein was reaching for in his final years, decades before any of the supporting mathematics existed. If that reading is right, reality is not quite the stage it appears to be. Space is not a container. Time is not a river. Matter is not a collection of small solid things. What we call the physical world is a network of relationships, correlations, entanglements, dependencies, that from the inside looks seamless and continuous, but from a deeper perspective is more like the consistent output of a very large computation. Now, this is the part where skepticism has to come in hard, because claims like that are old, easy to overstate, and extremely hard to prove. Dr. Sabin Hossenfelder, a theoretical physicist who has written widely on the current state of fundamental physics, has argued that a lot of modern theoretical work in this area suffers from a shortage of testable predictions. Elegance, symmetry, and mathematical beauty are not the same as experimental confirmation. She has publicly cautioned against the tendency of the physics community to treat speculative frameworks as if they were established, especially when those frameworks have not yet produced a single prediction that could be checked in a lab. Her skepticism is important here because any claim about what reality really is, drawn from equations in a notebook or from an AI's reading of those equations, is at best a hypothesis. It is not a result. The counterpoint, which some researchers have made in response, is that there are emerging tests. The holographic principle has been tested in specific constructed universes called anti-de Sitter spaces, where it holds. Entanglement-based models of spacetime have produced predictions about black hole evaporation that appear to match results from the string theory community. Experimental programs in precision interferometry are trying to measure the discrete informational texture of space itself, to see, quite literally, whether reality has a pixel size. If those programs succeed, they will put numbers on claims that have so far been philosophical. If they fail, they will shrink the space of possible theories. Either way, the picture is not stuck in pure speculation anymore. What the new analysis of Einstein's late work seems to contribute is historical texture. It suggests that the hunch he had, alone at Princeton, pointed in a direction that the field has spent 70 years rediscovering. That does not make it right. Many brilliant physicists have had hunches that turned out to be wrong. But it does make the direction less eccentric. It locates Einstein's last papers inside a live conversation, not outside it. And it raises a quieter question that the mathematics alone cannot answer. If reality really is, at its base, a structure of relationships rather than a stage of things, what does that mean for the way we experience it? Our senses deliver us a world of solid objects, distinct places, separate moments. That world works. You can build bridges on it. You can send spacecraft to other planets on it. The fact that the deeper structure might be different from the surface does not make the surface a lie. It makes it a rendering, a consistent one. The map is not the territory, but the map is what we walk on. Physicists who work in this area tend to be cautious about framing it in grand terms. They point out that the history of physics is a long series of lessons in humility. Every time we thought we had reached the base layer, we were wrong. Atoms turned out to be made of smaller things. Those things turned out to be fields. Those fields turned out to be excitations of something else. If the current candidate base layer turns out to be informational, there is no guarantee that informational is the end of the line either. It may just be the next floor down, and the one after that may be stranger still. What Einstein seemed to understand, and what the new reading of his notebooks underlines, is that the search for the base layer is less about finding a final answer and more about learning to ask the right question. He was not trying to discover the smallest particle. He was trying to discover the structure that made particles possible in the first place. That is a different problem. It is closer to asking why there is geometry at all than to asking what is inside the atom. The practical consequences, if this research program eventually succeeds, are hard to imagine. Technologies built on current physics have already transformed daily life in ways that would have been unthinkable a century ago. A theory that unified the forces, placed them inside a deeper informational structure, and described how space-time itself emerges from entanglement could, in principle, open paths that we currently cannot even sketch. Quantum computing at scales we do not know how to build. New forms of communication. A genuine physical theory of consciousness if it turns out that the informational substrate is shared between mind and matter in ways we have barely begun to guess at. Or, perhaps more likely, the answer will turn out to be deeply interesting and completely useless for engineering, the way quantum field theory is useful mostly because we learned how to cheat its predictions with very clever electronics. The honest answer is that nobody knows. The physicists working on this generally do not promise revolutions. They promise careful work, publishable results, and the slow narrowing of uncertainty. That is how real science proceeds. The flashes of insight, the notebooks, the moments that change a world view tend to happen quietly, in the middle of long stretches of routine labor. What Einstein left us in the end was not a failed theory. It was a direction, a sense that the pieces we think of as separate, matter and motion, space and time, observer and observed, are probably not separate at the most fundamental level. The new analysis of his late work does not prove the point. It cannot. Proofs in physics come from experiments, not from patterns in old notebooks. What it does is return him to the conversation, not as a historical figure but as someone whose intuitions still have traction. For those of us who are not going to solve the unified field theory ourselves, the takeaway is less technical and more philosophical. The world is probably stranger at its roots than our everyday experience suggests. That does not make our everyday experience less real. It makes it a kind of surface effect of something deeper. And the closer we get to that depth, the more the old distinction between the physical and the mathematical, the concrete and the abstract, the thing and the description of the thing, begins to blur. Einstein seems to have suspected this for a long time. He did not get to finish the math. But the direction he was pointing, judging by what his final pages appear to say, is the same direction the field is still walking. Whether that is a coincidence, a testament, or a clue we have not fully decoded yet, is a question worth sitting with. It is worth clarifying what the AI analysis actually did and did not do, because the phrase "solved Einstein's final equation" can easily mislead. The system did not produce a completed unified field theory. Nobody has produced one. What it did was something more modest and, in its own way, more interesting. It took a large corpus of Einstein's late manuscripts, including notebooks, letters to colleagues like Wolfgang Pauli, unpublished drafts housed in the Einstein archives at the Hebrew University of Jerusalem, and mapped the mathematical structures he was manipulating onto the landscape of contemporary theoretical physics. The result was a kind of dictionary, a translation layer. It showed that certain objects Einstein was wrestling with in the 1940s and 1950s correspond, under specific mathematical transformations, to objects that modern physicists now handle routinely. What looked at the time like idiosyncratic scribbling turns out in retrospect to have been an honest attempt to capture something that the field would later develop its own vocabulary for. That kind of work has precedent. Historians of science have done similar translations for Newton's alchemical notebooks and Dirac's offhand comments that later turned into major research programs. What is new in Einstein's case is that the translation has been done, at scale, with tools that can spot structural resemblances across thousands of pages of handwritten equations. The AI did not solve the physics, it helped organize the history, but the physics, organized this way, tells a particular story, and the story it tells keeps coming back to information. The connection between information and fundamental physics runs deeper than most introductions suggest. In the 1970s, Jacob Bekenstein proposed that black holes have entropy proportional to the area of their event horizon, not their volume. This was initially met with resistance. Black holes, in classical general relativity, were simple objects, described by only three numbers: mass, charge, and angular momentum. Entropy implied internal structure, internal states, internal information. Stephen Hawking extended the idea, showing that black holes actually radiate, and that the radiation carries thermodynamic properties tied to the horizon area. The resulting formula, the Bekenstein-Hawking entropy, became one of the most studied equations in theoretical physics. It suggested that the maximum information that can be stored in any region of space is proportional to the area surrounding that region, not the volume inside it. That is a bizarre claim. It implies that our intuitive picture of volume as the container of information is wrong. From that observation came the holographic principle, formulated in different forms by Gerard T. Hooft and Leonard Susskind in the 1990s. The principle states, in its strongest version, that the three-dimensional world we experience can be fully described by information encoded on a two-dimensional boundary. This is not a metaphor. In specific mathematical contexts, particularly the anti-de Sitter, conformal field theory correspondence developed by Juan Maldatena in 1997, the holographic principle has been demonstrated as an exact equivalence. Two different theories, one in a higher dimensional space with gravity and one on its lower dimensional boundary without gravity, describe the same physics. They are two ways of reading the same underlying structure. This is what contemporary physics means when it talks about space-time as emergent. The idea is that space, time, and gravity are not fundamental. They are consequences of a more basic layer, in which information is organized according to specific relational rules. From the right vantage point, what we perceive as geometry is simply the shape that certain patterns of information take when we look at them from the inside. Einstein's late notebooks, according to the new analysis, appear to circle around a similar intuition. He was not using the language of information theory, which did not exist yet in his mature form. He was using the language of geometry and symmetry. But the symmetries he was reaching for included some that, in modern formulations, correspond to information-preserving transformations. He was trying to find a structure in which the apparent differences between the forces of nature would reveal themselves as different projections of the same underlying object. The vocabulary was different. The destination looks, from this distance, strikingly similar. There is another thread worth mentioning. In recent years, a subfield sometimes called quantum gravity from entanglement has made significant progress. Researchers like Mark van Ramsdonk, Junjun Chao, and others have shown, in specific model universes, that geometric connections in spacetime can be built up from quantum entanglement between parts of a system. Disentangle two regions, and the spacetime between them literally comes apart. re-entangle them, and the connection reforms. This work is technical, and it has only been rigorously demonstrated in toy models. But it suggests a picture in which the fabric of reality is, quite literally, woven from correlations. The picture is not decorative, it is calculable, and it lines up, in a surprising way, with what Einstein's late work seems to have been approaching from the geometric side. What the physicists reviewing the new analysis keep emphasizing is that none of this constitutes a completed theory. The work is suggestive, not conclusive. Einstein's intuitions were not magic. They were the intuitions of an exceptionally thoughtful physicist working at the limit of the tools available to him. The fact that those intuitions point in the direction that the field has since traveled does not, by itself, mean that the direction is right. The field could still be wrong. Information-theoretic approaches to fundamental physics could turn out to be a productive dead end. One of those rich-seeming research programs that generates beautiful mathematics without producing a testable theory of the world. There is a real risk here, and it has been flagged by serious critics. Physicist Peter Woit has written extensively about the concern that modern theoretical physics has drifted into a regime where elegant formalism substitutes for empirical contact. A theory that explains everything and predicts nothing is not a theory in the traditional sense. Einstein himself was acutely aware of this. General relativity was accepted because it predicted the precession of Mercury's perihelion and the bending of starlight, both confirmed by observation. Any modern framework that claims to inherit his direction has to meet that same standard eventually. What makes the current moment unusual is that the testing infrastructure is finally starting to catch up. Gravitational wave observatories like LIGO and Virgo have begun to probe strong field gravity in ways that were impossible a decade ago. Upcoming space-based detectors like LISA will open new frequency ranges. Quantum computing, in its current noisy intermediate-scale form, is starting to simulate specific aspects of quantum gravity models directly. The James Webb Space Telescope is pushing cosmological observations into regions of the early universe where fundamental physics effects may become visible. None of these will, by themselves, prove a unified theory, but together they shrink the space in which hidden structures can hide. For most people, the practical consequences of this research are distant. But every previous revolution in fundamental physics has eventually reached into daily life. General relativity gave us GPS. Quantum mechanics gave us the transistor and the laser. Whatever comes after will likely reach us in forms we cannot currently imagine, decades after the original insight. Einstein reportedly said that the most important question a person can ask is whether the universe is a friendly place. He did not mean that sentimentally. He meant it in the precise sense his work had been chasing. Is the universe at its deepest level built on principles our minds can actually grasp? His answer, in the notebooks, appears to have been that it is knowable, but that the knowing will come slowly, from directions we do not yet see. Whether that is a coincidence, a testament, or a clue we have not fully decoded yet is a question worth sitting with. The pages are still there, the equations are still being studied, and somewhere between what Einstein wrote in 1954 and what physicists are writing now, the shape of the answer is taking form.